Hello. Today we're going to be having a look at the second part of the radiation topic in National 5 Physics. We're going to be looking at some problem-solving areas, looking at activity, dosimetry, and half-life. So, let's get started. Activity, first of all. What is activity? Well, activity is the number of nuclei within a radioactive source decaying per second. It's measured in a unit called becquerels. And it has the formula A equals N divided by T, where A stands for the activity in becquerels, N is the number of decays that are happening, and T is the time over which that number of decays occur, measured in seconds. So here's an example. A radioactive source is found to release 2,400 decays in 1 minute. What is the activity of the source? So, like in any problem-solving question like this, we start with our formula, A equals N divided by T. Now, we insert our numbers into that formula. N is 2,400, and T, the time, is 1 minute. But we have to remember that becquerels is the number of decays per second. Activity is measured in becquerels, or decays per second. So we need to convert our 1 minute into seconds, so it becomes 60 seconds. So 2,400 divided by 60, which gives us an activity of 40 becquerels. The next quantity that we have to deal with is what's called absorbed dose, and that has to do with living tissue absorbing radiation. So, the definition of absorbed dose is a measure of the nuclear energy absorbed per kilogram of tissue. It's measured in grays, or joules per second. And we can write the formula as D equals E divided by M. D is the absorbed dose, measured in grays. E is the energy, measured in joules. And M is the mass of tissue that's absorbing that energy of radiation, measured in kilograms. So, an example. A body part of mass 1.5 kilograms is exposed to radiation and absorbs 0.9 joules. Calculate the absorbed dose by that body part. So again, we start with our formula, D equals E divided by M. Our energy is 0.9 divided by our mass, which is 1.5, and that gives us an absorbed dose of 0.6 grays. Typically, the absorbed dose is a very small number, so it might be measured in milligrays or micrograys. Now, absorbed dose doesn't tell us much about how dangerous the radiation is. It tells us how much energy we're absorbing, but different types of radiation have different ionizing densities, as we know, and therefore can have different effects on our living cells. Now, the equivalent dose takes these differences into account. The equivalent dose is a measure of how harmful a particular dose of radiation could be. And it depends on the type of radiation being absorbed and on the absorbed dose. So how much you're absorbing, but also what type of radiation you're absorbing. It's measured in sieverts, or SV for short. And this is the formula for absorbed dose. H equals D times WR. So H is equivalent dose, measured in sieverts. D is absorbed dose, which we've already met, measured in grays. And this last term, WR, is called the radiation weighting factor. And that is what tells us about the type of radiation. Now, this radiation weighting factor is basically a measurement of uh, how how dangerous a type of radiation is if we absorb it. So alpha, because it's the most ionizing, has the largest radiation weighting factor of 20. This table that you can see on the screen here is given in the datasheet on the inside cover of your exam paper, and it tells us the weighting factor for each different type of radiation you're likely to come across. So, here's a question. A nuclear power worker receives the following absorbed doses in 1 year: 30 milligrays from gamma radiation and 250 micrograys from alpha. Calculate their total equivalent dose in the whole year. So, we've got two different types of radiation. So we need to figure out what is the equivalent dose from each type of radiation and then total it up at the end. So, first thing we need to know is the radiation weighting factor of each type of radiation. The little table on the right here is the one that's in the datasheet in our exam. And we can see we've got gamma radiation, which has a weighting factor of 1, and alpha radiation, which is a weighting factor of 20. So let's calculate these equivalent doses. So gamma, first of all, using the formula H equals D times WR. The absorbed dose for the gamma is 30 milligrays, so that's 30 times 10 to the power of minus 3, multiplied by the weighting factor for gamma radiation, which from the table we can see is 1, and that gives us an equivalent dose of 30 times 10 to the power of minus 3 sieverts, 30 millisieverts. Now we're going to do the same for the alpha one. So same formula, H equals D times WR. This time, our absorbed dose is 250 micrograys, so 250 times 10 to the power of minus 6, times the weighting factor for alpha. From the table, we can see alpha is 20, and that gives us an equivalent dose of 5 times 10 to the power of minus 3 sieverts, or 5 millisieverts. Now, the total equivalent dose is going to be the sum of those two added together. So 30 times 10 to the power minus 3 plus 5 times 10 to the power minus 3, which gives us 35 times 10 to the power of minus 3 sieverts, or indeed 35 millisieverts. Now, there are some numbers that we have to be aware of as far as equivalent dose goes, and these are to do with dosages. The first one is the annual effective background radiation in the UK, which is about 2.2 millisieverts per year. That's an average because depending on where you live, it might be a little higher or a little lower. But we do have to remember that number. Background radiation in the UK, 2.2 millisieverts per year. And there are also some dose limits set by the government. The first is for a member of the public, so just a standard normal person that's not doing anything normally with radiation in their normal everyday life. They should receive no more than 1 millisievert per year over and above their normal background dose. If you happen to be a radiation worker, that being somebody who works in a nuclear power station or in a nuclear submarine, or you work in a radiography lab in a hospital perhaps, then your equivalent dose limit is a bit higher because you're going to have your situation monitored a bit more rigorously. And for a radiation worker in the UK, the radiation limit for them is 20 millisieverts per year over and above normal background. Now, another thing that affects how quickly or how dangerous radiation can be is how quickly you absorb it. So, a small amount of radiation absorbed very quickly can be as dangerous as a large amount of radiation absorbed over a lifetime. And to take into account this, there's this other quantity called equivalent dose rate. Equivalent dose rate is a measure of how quickly an equivalent dose is accumulated. It has this formula: H dot equals H over T, where H dot is the equivalent dose. It's basically the equivalent dose divided by time, and it can be measured in sieverts per second or sieverts per hour. Now, the final part of these problem-solving areas in radiation is looking at a thing called half-life. Now, the half-life of a source is the time taken for the activity of the source to fall to half of its original value. So, what happens as a radioactive source decays? Over time, the number of atoms left to decay decreases, and therefore the rate that it decays decreases as well. And the time it takes for the radiation to drop to a half of its original level is the same as the time it takes to go from a half of its original level to a quarter of its original level, which is the same as the time it takes to get from a quarter to an eighth of its original level, which is the same as the time it gets from an eighth to a 16th, and so on. It's a consistent time, and that time is known as the half-life. So, for example, here's a graph showing us the count rate of a radioactive source over a period of 10 days. And we can see at the beginning it starts at 80 counts per minute. So, half of 80 is 40. And we can see it reaches 40 counts per minute after 2 days. Half of 40 is 20. And it reaches that after 4 days, another 2 days. So it goes from 40 to 20 in another 2 days. Half of 20 is 10, and it reaches that after 6 days. Again, another 2 days. So we can see from this graph that the half-life of this particular radioactive source is 2 days. Now, we have to be aware of an experiment that we could do to measure the half-life of a radioactive source. So, we're aiming to measure the half-life of a radioactive source. So what we would do is we would set up our source with a Geiger-Müller tube focused on it, attached to a rate meter. And what that's going to do, well, we're going to measure the background count rate over a period of 1 minute 3 times to obtain an average background count rate. Because we need to know the corrected count rate. We need to know what is entering that Geiger counter that is due only to the radioactive source we're investigating, not due to the background level as well. Secondly, we're going to measure the activity of the source over 1 minute every 5 minutes for a period of time. Then we're going to subtract the background count rate from each reading to obtain the corrected count rate, and then plot a graph of the corrected count rate against time to determine the half-life of the source. So, we measure our background count level. We get 31, 33, and 29 when we do it 3 times. And then we take these results. So we've got the time from the start. At 0 minutes, the count rate is 675. At 5 minutes, it's 570, and so on. Now we need to do our little bit of analysis of this. So I've done this using a spreadsheet. So down the left-hand column, we can see the time in minutes. Down the middle column, we can see the count rate that we measured. And then on the right-hand side, we can see the corrected count rate. Now, the corrected count rate was obtained by subtracting the average of those background radiation levels from the original count rate. So, the average background count level, incidentally, was 31 counts per minute. So 675 minus 31 gets us 644. 570 minus 31 is 539, and so on. And then I've asked my spreadsheet to draw me the graph on the right-hand side, which shows the count rate, the corrected count rate against time. And from that, we can work out the half-life. So our original count rate was just around about 640, as we can see on the graph there. Half of that is 320, and it reached that after a time of about 18 minutes. Then half of that, and then half of that. So I've repeated that 3 times, and I can measure the half-life each time. So it turns out that the half-life of the source is a pretty consistent 18 minutes. Now, some other examples that we have to do with half-life. First of all, the activity of a source falls from 80 megabecquerels to 5 megabecquerels in 8 days. Calculate its half-life. So, we know the original activity is 80 megabecquerels. Now, every time the activity halves, that is one half-life having occurred. So, it halves from 80 down to 40 after one half-life, 40 down to 20 after two half-lives, 20 down to 10 after three half-lives, and then 10 down to 5 megabecquerels after 4 half-lives. So, it got from 80 to 5 in 8 days. Therefore, 4 half-lives occurred in 8 days. So, one half-life will have occurred in 8 days divided by 4 half-lives, which is 2 days. So the half-life of this source must have been 2 days. The other type of question that you might be asked is, knowing the half-life, what is its activity going to be after a certain amount of time? So a source has an activity of 200 kilobecquerels. If it has a half-life of 4 months, what would its activity be after 1 year? So, 200 kilobecquerels. Well, at the beginning, at the start, after no months have passed, the activity is 200 kilobecquerels. After 4 months, which is one half-life, its activity will have halved to 100 kilobecquerels. Another 4 months, and its activity will have halved again. So after 8 months, it's 50. Another 4 months, 12 months, 1 year, which is what we're interested in, its activity will have halved again to 25 kilobecquerels. So after 1 year, the final activity is 25 kilobecquerels. So that's just a run through of the various different types of problem solving questions you might be asked about and the different formulas that you have to be aware of for the radiation topic at National 5 Physics. Why don't you have a go at the related video which takes us through some past paper questions about these topics and see how you get on. Until next time, bye for now.